One of the most intriguing aspects of astronomical events is the possibility of a supernova, Betelgeuse, located in the famous shoulder of the constellation Orion, is a massive red star nearing the end of its life cycle. Interestingly, in 2019, one of the sky's brightest stars began to dim. Being clearly visible to the naked eye, its brightness decreased so dramatically over several months that many observers wondered if the star was dying. Scientists studying giant stars turned their telescopes toward Betelgeuse and were astonished by evidence of the great dimming. Betelgeuse is believed to be close to exploding into a supernova, marking the end of its life cycle. But when and why will the stellar explosion occur? Could it have devastating consequences for Earth? The glowing ruby star, Betelgeuse, lies on the upper right shoulder of Orion the Hunter. You may recognize it by its other name, Alpha Orionis, although it is the second brightest star in its constellation, behind the supergiant Rigel. It remains one of the most interesting to astronomers because of its variable behavior and peculiar name. Alpha stars are usually the brightest stars in their constellations, and although Rigel outshines it in brightness, Betelgeuse stands out for its size and reddish color. Betelgeuse, also known as Alpha Orionis, is one of the most famous stars in the night sky, the 10th brightest and 7th brightest visible from much of North America, Europe, and Canada. Its name comes from Arabic and means armpit of the La, giant, in reference to its position in the constellation. Betelgeuse loses about 1 solar mass every 10,000 years, ejecting material uniformly in all directions and forming a nebula around it. This nebula has a diameter of 30 astronomical units, 30 times the distance between Earth and the Sun, and is 250 times larger than the star itself. At its core, Betelgeuse's hydrogen atoms fuse under immense gravity, producing helium and releasing light and heat. As the star exhausts its hydrogen, it begins to fuse helium and carbon as fuel. When the helium is consumed, neon reacts with carbon to form iron. The fusion of iron releases no energy, causing the star to collapse under its own gravity and eventually explode in a supernova, one of the most powerful explosions in the universe. Depending on their age and evolutionary stage, stars emit light in different wavelengths, from the bright blue of new stars to the red of older ones. According to the ancient astronomer Ptolemy, Betelgeuse had a color he described as ruddy. However, ancient Chinese astronomers noted that Betelgeuse appeared yellow, suggesting that it may have once been a yellow supergiant. Large stars tend to consume their hydrogen rapidly, bringing them to a premature end, even if they only live 10 million years. There is no doubt that Betelgeuse is in the final stages of its existence. While our Sun has more than 5 billion years left, Betelgeuse is getting close to dying, which means it might, at some point, explode as a supernova. However, the exact timing of this event remains uncertain. Betelgeuse goes through 2 brightening and dimming cycles, one of which occurs every 5 years and lasts about 100 days. It is thought that the growth and contraction of its outer shell during these cycles cause changes in its diameter and average temperature. Many focused on Betelgeuse as a result of its erratic behavior in 2019 and 2020, when its brightness decreased dramatically, only to briefly recover. Some astronomers speculated that this behavior could indicate the star is nearing the end of its life. Detailed studies of Betelgeuse date back to the 1st century BC, but the cause of its dimming remains a total mystery. Betelgeuse has been detected moving through the interstellar medium at a speed of 30 km/s after being ejected from its place of origin in the Orion OB1 association which contains the stars of Orion's belt. The shock arc from this movement extends more than 4 light-years. Determining the distance to red supergiant stars like Betelgeuse is notoriously complicated in astronomy, as multiple factors make it difficult to calculate its exact position and size. As a pulsating star, Betelgeuse's diameter changes over time. This phenomenon, combined with stellar limb darkening, causes its visual emission to change color and dim as we move away from the star's center. Additionally, the envelope around the star, consisting of the debris it has released, plays a crucial role in producing and absorbing light, which also influences how we perceive its brightness. Direct comparisons between observations of Betelgeuse are difficult, as its apparent size varies depending on the wavelength used. Diameters can change as much as 35% depending on the wavelength used to measure them within the electromagnetic spectrum. In July 2009, the European Southern Observatory published images captured with its VLT interferometer ground-based telescope, displaying an enormous plume of gas extending up to 30 astronomical units from the star's atmosphere. This was one of multiple mass ejections observed from Betelgeuse. The ejection was comparable in size to the angular separation between the Sun and Neptune. At least 6 such ejections have been discovered. This phenomenon may offer clues to the mystery of mass loss in the final phases of giant stars, an important factor in the complex dynamics that lead to their demise. The processes behind Betelgeuse's extended atmosphere remain an enigma, as does the exact mechanism by which material is ejected from red supergiant stars. These ejections are crucial for the recirculation of matter in galaxies. Thanks to advances in interferometric techniques, astronomers are closer to solving this enigma. In 2019, researchers using the Hubble Space Telescope and other instruments discovered that Betelgeuse had ejected a large portion of its visible surface, generating a significant surface mass ejection, SME. Although the Sun produces coronal mass ejections, the events observed at Betelgeuse were thousands of times more intense, ejecting an amount of a substance 400 billion times more massive than a typical coronal ejection from the Sun. This explains why Betelgeuse experienced a rapid decline in brightness in October 2019. By the middle of February 2020, it had lost about 2/3 of its luminosity, going from magnitude 0.5 to 1.7. By February 17, 2020, Betelgeuse's brightness had remained relatively constant for over a week. On the 5th, it appeared that the star had stopped dimming completely. Nevertheless, the most recent visual fades were not related to a possible collapse of its core, due to the absence of significant infrared changes. These were observed on February 24, 2020. Let me know what you think in the comments box. Click the like button if you enjoyed the video, and subscribe to avoid missing out on more content like this one. When Betelgeuse finally explodes in a supernova, it will be one of the most spectacular celestial events in recorded history. Despite being 640 light-years away, the explosion will be so bright that it could outshine the full moon in our night sky, and even be visible during the day for weeks or possibly months. Astronomers estimate that the supernova will release more energy in a matter of seconds than our Sun will emit during its entire 10 billion-year lifespan. The light from the explosion will race across space and eventually reach Earth as a brilliant point of light unlike anything we've ever seen. But don't worry, we're completely safe. While a supernova that close might sound dangerous, Betelgeuse is still far enough from Earth that the blast won't harm our atmosphere or life. What it will do, however, is provide a first-of-its-kind scientific opportunity. As of recent years, Betelgeuse is back to its previous levels of brightness, but its irregular dimming cycles continue to be monitored closely. Scientists are using instruments similar to the James Webb Space Telescope, the ground-based Hubble Space Telescope, and interferometers like VLT and ALMA. They're observing fluctuations in surface brightness, convective cell patterns, and the ongoing mass loss, events that seem to signal the star's instability. One common hypothesis is that Betelgeuse's great dimming was caused by a massive cloud of stellar dust created during one of these outbursts, temporarily blocking the star's light from our perspective. Comprehending Betelgeuse could help astronomers unravel the life cycles of massive stars, especially those nearing supernova. This knowledge could assist us in understanding similar events in other galaxies, the chemical enrichment of the universe, and how elements such as iron and gold are created and distributed throughout space. Betelgeuse is essentially a stellar time bomb, and it's ticking slowly. It may explode tomorrow, next year, or in 100,000 years, but whenever it does, it will offer us a cosmic light show and a scientific treasure trove. Unlike anything in recent memory, Betelgeuse continues to be one of the most closely observed stars in modern astronomy due to its unpredictable behavior and its potential to become a nearby supernova. Although the timeline remains uncertain, the inevitability of its explosion is accepted by scientists. What continues to intrigue researchers is not just when it will happen, but how the process will unfold in real time, offering insights that cannot be captured through observations of more distant or ancient supernovae. This proximity allows for high-resolution monitoring of every fluctuation in light, temperature, and surface activity, making Betelgeuse a fantastic natural laboratory for studying stellar death. As instruments become more precise, astronomers now have the ability to detect minute changes in the star's photosphere, the layer that gives off light. These changes often reflect internal processes that are not yet fully understood. The fluctuations in temperature and brightness are believed to be caused by massive convective cells, essentially enormous plasma bubbles, that rise and fall on the star's surface, causing significant changes in how it appears from Earth. These surface patterns can span a significant portion of the star's diameter and can evolve over weeks or months, contributing to the star's irregular light curve. Another factor contributing to the complexity of studying Betelgeuse is its rotational behavior. Unlike smaller, more stable stars, Betelgeuse rotates slowly and unevenly. This uneven rotation influences how material is distributed in its outer layers and contributes to chaotic mass ejection events. Each time the star sheds part of its atmosphere, the surrounding space becomes enriched with heavier elements, influencing the formation of future stars and planets. The remnants of these ejections also form clouds of dust and gas that scatter and influence the star's behavior by absorbing light and altering how it appears in different wavelengths. According to simulations, the star may already be in the late stages of fusing heavier elements like silicon, which occurs shortly before the collapse of the core. If true, this would mean that Betelgeuse is much closer to the end of its life than previously thought. However, the margin of error in such models is significant given the vast scales of time and the unpredictability of massive stellar evolution. Astronomers continue to refine these models, using data gathered throughout the electromagnetic spectrum, from ultraviolet to infrared, to improve estimates about the star's internal processes. The eventual supernova of Betelgeuse will not only be a spectacular visual event, but also a monumental scientific one. The neutrinos, gravitational waves, and electromagnetic radiation released will provide multiple layers of information about what happens during a supernova in near real time. Telescopes around the world, as well as in orbit, are already prepared with observation protocols designed to immediately react to the first signs of collapse. In the meantime, scientists remain vigilant, using every tool at their disposal to understand this stellar giant. Each observation brings humanity closer to understanding not only the fate of Betelgeuse, but also the life cycle of stars as a whole. The death of such a massive star is not merely an end, but a beginning, seeding the cosmos with the elements necessary for life and preparing the way for the formation of new stars and planets in the far future.